So today's webinar is going to cover some fairly simple topics. Those of you who are already familiar with the contaminant transport module in GoldSim will probably find it a bit boring. We're just going to cover some very, very simple topics in the contaminant transport module. This webinar is really intended to introduce the contaminant transport module to folks who haven't used it before, using a specific application, which is just simple mixing calculations. We're not going to do chemistry or partitioning or solubility. We're just going to show how to use the contaminant transport module to do some simple mixing calculations. Before we get started here, we've got a pretty big group, so everybody's muted, otherwise it would be a bit loud. If you do have a question, however, you can type it into the little chat box, and either during the webinar or at the end, I'll look through the questions and answer them. So let's go ahead and get started. So just to keep in mind, the basic GoldSim framework is really generic. The tools are very abstract, like a programming language. And for those of you who perhaps have used GoldSim to do water management calculations, you'd understand this. This webinar, by the way, assumes that you're familiar with the basic GoldSim frameworks, that you've played around with the basic part of GoldSim a bit. So even though the basic GoldSim framework, you can do a lot of things with it, there's certain types of calculations that would be difficult to do in a very abstract tool. And so we created a number of specialized extension modules to make it easier to simulate certain types of systems. And in particular, the contaminant transport module is one of these. And it was added to support the simulation of contaminant transport, the movement of contaminants, of chemicals through the environment or through engineered systems. So what this module does is it predicts things like mass transport rates at defined locations, concentrations, in specified media, water, soil, sand, and impacts to human receptors. There's lots of power behind the contaminant transport module. You can do things like simulate solubility, partitioning onto solids. You can simulate the movement of particulate matter, advection and dispersion, diffusion, chemical reactions, radioactive decay and ingrowth. So there's a lot there. We're just going to focus on pretty much the basic use of the contaminant transport module, and that's to just do simple mixing of waters. So mixing different waters and seeing what the resulting concentrations are. So you might use this in a stream. You might use this in a system of ponds or lakes, various surface waters. So we're just going to walk through some simple examples that just show how you can use contaminant transport module for mixing, just to get your feet wet, so you can get used to using this tool. Once you understand that, then you can start to learn more about all the other powerful things that the contaminant transport module can do. So I'm going to start, again, this is really focused on those of you who have never used the contaminant transport module. Just going to give you a really quick overview in about five or 10 minutes of what the contaminant transport module is all about, what it looks like. And then we'll spend the rest of the webinar, I'll just walk you through a series of example models that do some simple mixing calculations. So what the contaminant transport module does, it actually adds a number of elements to GoldSim. So when this contaminant transport module is turned on, there's a number of elements that are added to GoldSim. This is just a few of the elements. And these elements are used to build basically contaminant transport simulations. What the contaminant transport module really does is just it provides a basic framework for simulating the movement of mass through an environmental or engineered system. Like the rest of GoldSim, it's very flexible. So you can build a very simple model in a day or two, or you can work on a model for months. It incorporates some basic physics. Obviously, we're doing contaminant transport, so we're going to do conservation of mass. You can decay and ingrow species, basically chemical reactions. It understands diffusion, chemical partitioning. So there's some basic physics that are built into it, which is very different than the basic GoldSim framework, which is just some mathematical tools. In this case, the contaminant transfer module understands the advection dispersion equation, for example. It understands the diffusion equation. So those are built into it to allow you to do these type of calculations. But besides that, there's very few assumptions that are built into the code. We want to make it very flexible so you can simulate almost any system you want to. One thing about the contaminant transfer module that's quite critical is it heavily uses arrays. So if you've used basic GoldSim, you may have noticed that in addition just to dealing with scalars, you can also create arrays, one-dimensional arrays and two-dimensional arrays. The contaminant transfer module relies on that heavily. Basically, it deals with arrays of species because we're moving different species through the system. We're going to take advantage of this capability in GoldSim to model multiple species simultaneously. So the way you go ahead and build a contaminant transport simulation in GoldSim is you walk through these steps. You define what species you want to model. You then define some transport and storage media. So this would be things like water, sediment, soil, rock. These are actually the media in which contaminants are stored and or transported. And then you build some transport pathways. Transport pathways made up of media. It could be an aquifer. So an aquifer might be made up of water and sand. Could be a lake, which could be made up of water and sediment. Could be a tank, which just may have water in it. And then you hook those transport pathways together to move mass through the system. Of course, you also have to define some source terms, and ultimately you often want to define the impact of these species on defined receptors. So you might want to convert a concentration to a dose. We're not going to talk about these things in detail today. We're really just going to focus on setting up some species. The only media we're going to deal with is water, and we're going to build a few transport pathways to illustrate how GoldSim carries out some mixing calculations. So the way the species work is there's an element in GoldSim called the species element, and you list the species that you wanted to simulate. You just type them in, and GoldSim doesn't know anything about these species. So here I've created two species called C and D. Typically, they would actually represent real species, species that zinc or cadmium or iron. One version of the contaminant transport module deals with radioactive isotopes, the radionuclide transport module. And that particular module is a little bit more powerful. It actually has a built-in database of all the isotopes and has half-lives built in and so on. But for basic GoldSim, the contaminant transfer module, you're just going to enter a species. You're going to make up the name of a species. Say this is a species I want to simulate. You're then going to build some environmental media, and there's really two types of media in GoldSim. You can have a fluid and you can have a solid. You can have multiple fluids in a model, so you could have water and air and oil, and you can have multiple solids: sand, clay, rock, soil. The models we're going to build and look at today are just going to have water. We're just going to look at mixing of water. So all of our pathways are only going to contain water. We're not going to talk about solids that are also present in these pathways. We're just going to look at mixing of water. So when you do define these media, you have to give them some properties. Things like solubilities for water, or if it's a solid, things like a partition coefficient. Again, today we're not going to do either of those. We're going to assume everything is infinitely soluble and we have no solids, so we're not going to do any partitioning. We're just going to do some mixing models today. We're going to kind of start simple to kind of lay a framework for you that you can then build upon. So the transport pathways represent those parts of the system where we're going to transport or store our species. So if you're modeling a plant of some sort, these just might be a series of tanks. Each tank is a transport pathway. If you're modeling an environmental system, these transport pathways might represent ponds or reservoirs, aquifers, soil columns, could represent an atmospheric column. So there's basically those parts of the physical system where species are transported or stored. You have to define the properties of these pathways. How big are they? How much water do they hold? How much sand do they hold? How should I discretize them? And then you have to define the media that are inside these pathways. So if I were to define a pathway that consisted of a pond, I might say, well, this pond contains water and some sediment at the bottom of the pond. So I have to tell GoldSim how much water is in the pond, how much sediment's in the pond. So the way you should think about a transport pathway, this isn't actually mathematically correct. It's not, transport pathways aren't actually mathematically transfer functions, but it's a good way to think about them. A transport pathway basically is you're going to put some mass into it, some mass rate, right? Some mass as a function of time. Something's going to happen in there and it's going to spit out mass, and it's probably be delayed and dispersed a little bit. So that's really what a transport pathway is all about. When you create a system in GoldSim, you're going to hook a number of transport pathways together to track the movement of mass through your system. So you might have a soil pathway that discharges to an aquifer that then goes into some rock and then that gets pulled up into a water supply well. Each one of those parts of the system would be represented by a transport pathway. And there would be some mechanism by which mass moves from one pathway to the other. In most systems, the key mechanism is going to be advection. We're going to move water, for example. But there's other mechanisms that can move mass too, diffusion. And so that's typically how you're going to set up a transport pathway. We're just going to today deal with very, very simple transport pathway systems in which we're just going to advect some water from one location to another. So GoldSim actually has a number of different pathways. We're only going to do one. We're going to focus on a cell pathway today in the examples I'm going to show you. And as I said before, we're only going to consider water. There's no solids in this mixing cell, this cell pathway. The cell represents something like a tank or a pond, and it only contains water. So one last thing before we start working through some models about contaminant transport module itself, it moves mass through a system. All right, that's what it does. It actually simulates mass transport between these pathways. But in order to move mass through the system, we typically have to move things like water through the system. So GoldSim is going to conserve mass as it moves through the system, and it's going to solve for where the mass is in the system. It's not going to solve for where the water is in the system. You have to do that, right? So you would build a water management model or water balance model or water flow model using other elements in GoldSim, and they would then act as input to the contaminant transport part of your model. So we'll toward the end of the webinar, I'll show you an example of what I mean by that. Okay, so I've laid just some basic framework about what we're talking about in terms of the contaminant transport module. Now I'm going to show you just a series of examples so you can get a feeling for how it works. And again, we're going to focus just on simple mixing. We're not doing any chemistry. We're not doing any partitioning. We're not doing any complicated transport processes. We're just looking at the mixing of waters of different concentration and how GoldSim would carry out that calculation. And we're going to use cell pathways to do that. So a cell pathway is the simplest of the pathways, but probably the most powerful of the pathways. A cell pathway is a well-mixed cell. What this means is it's like a tank, all right? Any mass that goes into this pathway is instantaneously mixed throughout the pathway. It's not discretized. It's all mixed within that pathway. And if we had multiple media, which we won't in our examples, but let's say we had some water and soil, instantaneously the mass is partitioned between those media. That's how cell pathways work. We can do things like apply solubility constraints and do partitioning. We're not going to do that today. We're just going to address simple mixing without multiple media or solubility constraints. So let's look at a simple example. So in this example, what I'm going to be looking at is I'm going to have two inflows into a well-mixed tank. So I just have a tank. This tank holds 10 cubic meters of water. It's got no mass in it, zero concentration. And I have two inflows into the tank. Okay? I have a certain flow rate, 4 cubic meters per day of water, that has a certain concentration of some species named X. So 4 cubic meters of water with a concentration of X of 10 grams per cubic meter enters this tank. And simultaneously, 6 cubic meters of water with a concentration per day of water with a concentration of 2 grams per cubic meter enters the tank. So I have two flows coming into the tank. The total flow is 10 cubic meters of water. And we'll just assume the tank is filled, so any water that enters flows out. But because we're going to represent this by a mixing cell, we're assuming this is well mixed. So essentially what we're going to say is the water flows in from these two sources. It's instantly mixed throughout this tank, and then it flows out. So I want to know what the concentration in the tank is. And how do we do that in GoldSim? So let's look at the GoldSim model that does that calculation. Here's the GoldSim model. I'll just point out at the top of the GoldSim model, I have a species that I entered called X. That's all I've done. Just so now GoldSim says, okay, there's a species called X that we're going to be simulating. The actual model looks like this. So these are just basic GoldSim elements. We'll talk about those in a minute. Here is the mixing cell that represents the tank. So this is the mixing cell, part of the contaminant transport module that represents the tank. If I double click on that, the dialog is quite simple. The dialog says what media exist in this mixing cell. And in this case, it's just one medium, it's water. And how much water sits in the cell. And then I also, so that's how much water is in the cell. And now here I have to say, is there any mass coming into the cell from outside of the system? And in this case, I have a mass input rate. Remember, we have those two sources of mass entering the cell. We'll look at that in a minute. How much water is flowing out of the cell? Well, I'm flowing from the tank to something I just called sink, because I don't care. This leaves the system. It's a sink for my simulation. I'm going to flow from the tank at a rate of 10 cubic meters per day. So that's what I've got going on in this model. The rest of these are just simple calculations. So remember, I've got my total volume, I said, is 10 cubic meters. I have an inflow of 4 cubic meters and at a concentration of 10, and another inflow of 6 cubic meters per day at a concentration of 2 grams per cubic meter. So my total flow rate is just 6 plus 4. My mass input rate is just that, right? It's the inflow times the concentration plus the inflow times the concentration. That's how much mass is actually entering that tank. If I just wanted to do a simple calculation without the contaminant transport module, I could actually calculate, well, what's the steady state value? Well, the steady state value is pretty simple, right? The steady state value in a system like this is going to be the mass input rate divided by the flow rate. That's what your steady state value would be, and that turns out it's going to be 5.2. But our tank is going to look a little bit different, because remember, the tank starts empty. There's no concentration in the tank. So if we go ahead and run this model, we get a result that looks like this, right? So the tank starts empty, and it fills up, it fills up, it fills up, and it finally, at this point, it's reached a steady state. And of course, that steady state value is the 5.2, right? But it took, 6 days or so to get up to that steady state value. We'll talk about why it took 6 days to get to the steady state value in a minute. So that's a simple mixing model where I didn't have to do any calculations. I didn't have to write out equations. I just had to tell GoldSim, here's how much mass is coming in, here's how much water is flowing out, and GoldSim calculated the concentration for me. All right. So now let's move to something a little bit more complicated. Slightly complicated, really. All I'm doing here is, instead of the tank starting out with a concentration of 0, I'm going to say the tank initially has a concentration of 20 grams per cubic meter. Before it was 0 grams per cubic meter. Well, if we go back to this particular model, the first model I built, I said that when we set the model up, I had to tell GoldSim how much mass was entering the tank. And what I said is I just calculated a mass input rate and I put it in there. Now I want to do something a little bit different. Not only do I have mass coming in, but I also have an initial concentration in that tank. So that model is going to look a little bit different. That model is going to look like this. So I have very, very similar structure, but now instead of saying I have an input rate, what I'm telling GoldSim is I have a cumulative input. So what does that mean? What it means is, look, I've got two things going on in this tank. I have a mass rate coming in, and I also have an initial amount of mass. And so what I end up doing in order to simulate this in GoldSim, I actually use an integrator element. And I say, look, this is the cumulative amount of mass that has entered the pathway. It has an initial value of the initial concentration of 20 times the volume in the tank. That's how much mass was in the tank at the beginning of the simulation, 200 grams. Initial concentration times volume. And then I'm going to add mass at this rate. 52 grams per day. I integrate that, and that becomes the input for GoldSim. It basically says, I'm going to have a cumulative input into this mixing cell. This gives me the ability to specify both an initial mass and a mass rate in. That's all we've done differently. Everything else is the same. I run this model. We're going to get a slightly different simulation now. Remember, the thing started at 20, didn't start at 0. And I'm adding water, but I'm adding water at a lower concentration. It still eventually reaches a concentration of 5.2, right? That's the steady state value. But instead of starting from 0 and climbing up to 5.2, it started from 20, and basically I'm flushing the tank out of that high concentration, and then at steady state it reaches this concentration. So very simple model still, just a simple mixing model. Okay. Now let's think about the tank volume. How does the tank volume impact this simulation? Right? So in this model here, I had a tank volume. In both of these two models, the volume was 10 cubic meters. So I'm going to build another model in which I have the tank volume. I'm going to vary it. I'm going to have the tank volume vary between 0.1 cubic meter and 100 cubic meters. And let's see how that changes the results. What does it do? What is the importance of what the volume of that tank is? Does it change the steady state volume concentration? What does it actually change if I change that volume? So let's look at that model. And what that model looks like, and the way, by the way, the way I did this, I set my volume up using a selector, and I'm going to run 7 realizations, 7 Monte Carlo realizations. In each realization, I just use a different volume. So now I'm going to have basically 7 runs in which the volume changes from 0.1 to 100. And if I do that, and I went back to an initial concentration in the tank, by the way, of 0. If I do that, my result looks like this. So essentially what's happening here is this is the result when the volume was 100. This is the result when the volume was 0.1. And so you see what the volume does is the volume determines how long it takes this thing to reach a steady state. The volume says how long does it take for the average concentration, because remember we're mixing it through the whole tank to respond to these inputs. If I have a very small volume, it responds instantaneously, right? If I have a very large volume, obviously it's going to take a long time. I mean, if I start out with 100 cubic meters of concentration 0, it's going to take a long time for this stuff to bring the concentration up to the steady state value of 5.2. So that's what the volume does. The volume doesn't affect the steady state. In all these cases, my final steady state volume, my final steady state concentration is the same. Okay? What it changes is how quickly the concentration in this tank reacts. How long does it take to react? And that's got some important implications for kind of more realistic modeling. Okay? So to kind of illustrate that, we're going to do another model with the tank. And in this tank, I'm going to have a very small tank volume, all right, which means it's going to respond instantaneously, all right? And now I'm going to make the inflows a little bit more more complicated. I'm still going to have the same concentration. So one inflow has a concentration of 10 cubic meter or 10 grams per cubic meter. The other inflow has 2 grams per cubic meter, but I'm going to say the flow rate is a little bit different. So basically, I'm going to say the flow rate is bouncing around. It's not always 4. I'm going to simulate this as a stochastic. It's going to bounce around. This guy's going to bounce around 6. Okay. So let me just show you that model to see how I set that guy up. So here I just represented my flow rate as a stochastic variable with a mean of 4 and a standard deviation of 1. I'm resampling it every hour, right? So if I were to run this model, my flow rate, this is the first inflow, is just bouncing around. So it's not constant. My second flow rate also bounces around, okay? The tank volume still stays constant, because essentially the flow rate out of the tank is equal to whatever the flow rate in the tank. Physically, you could imagine the tank is full, and whatever water comes in flows out. So it's well mixed, and then it flows out. But I'm going to have some noise. I have a noisy input rate. So my mass input rate is actually noisy. That's what my mass input rate looks like. So let's look at what the concentration in the tank looks like. Well, as you can imagine, the concentration of the tank started at 0. It instantaneously responded, and then it just bounced around. So that's my concentration in the tank. It's around 5.2, right? That's what our steady state, we expected our steady state value to be, but we're bouncing around. So this is just, we're reacting to variability in these inflows. and GoldSim is calculating that, what the concentration is in the tank instantaneously, because it's instantaneously mixed, because our tank volume is so small. So what does this represent physically? Well, the way you should think about this is analogous to computing the concentration at a point in a river where two streams meet. Right? If you had two streams coming in at this flow rate and this concentration and this flow rate and this concentration, and you wanted to know what happened immediately downstream of where those mixed, this is how you would simulate that system. You'd basically define a very small volume, and the concentration in that mixing cell is the concentration just downstream of where those two streams mix. That's basically what this does. I'll show you, we're going to look at an example of that in a minute. But before we do that, let's do one more thing just to show you how easy this is to do in GoldSim. It's the same model we just did before, very small tank, stochastic inflow rate. But now what I'm going to do is, instead of having just one species, I'm going to have two. All right, so I've added a second species called Y, which is slightly different concentration. So the first flow, the first source, has 4 cubic meters per day of water flow. X is at 10, Y is at 1. And the second source has 6 cubic meters per day, more or less, of water flow. X is at 2, Y is at 3. So GoldSim makes it very easy to do that. So if I wanted to simulate that particular system, I essentially do the following. I come over here to where my species are, and now I've defined two species, X and Y. Well, that's a very important point. Now that I've got two species, I could create an input parameter, and I could make it a vector of species. And if I do that, GoldSim looks at the species list, and that's my list of species. So essentially, if you've used vectors before, arrays in GoldSim before, you have to tell GoldSim, if I'm creating an array, what is an array? What is an array of? You can define array label sets. When you use a contaminant transport module, the species element defines an array label set of the species that you've defined. So this allows me to operate on an entire array of species. Why is this important? Well, look what I've done here. I now have, this is my inflow. It's still just that stochastic, but my concentration is a vector of species. I said my concentration is 10 for X and 1 for Y in the first stream, and it's 2 for X and 3 for Y in the second stream. All right? By the way, that means my mass input rate is also a vector. So that's a scalar, that's a vector. A vector times a scalar times a vector produces a vector. So this is actually a vector of species, my mass input rate. My input into tank, that's a vector of species. All I needed to do was define those two species and put my inputs in here. This element will handle the species. I have 2. A realistic model might have 20. I don't need extra elements to model 20 species. I just treat them as a vector, and it moves them through the system. So if I run this model, I can actually plot all my results. So here I have, I'm looking at the concentration in the tank, but for both species. There's my X, this is what we were simulating before, and here's Y. So I can show a plot of the concentration of both species in that tank. And you can imagine in a real model, you're usually going to have multiple species that you're tracking through the system. Okay, so as I pointed out, modeling a very small volume like we've done here is analogous to computing the concentration at a point in a stream where two streams meet. And let me actually show you a model that does exactly that. So again, it's a very simple model. We're just trying to keep things simple for this webinar. But what I've got is a stream system where there's a reach here, a reach here. Those two reaches combine and mix here, and then they move on, and then move on. All right? Let's look at how we simulate any particular reach. So if we look at reach 1, okay, reach 1 is represented by a mixing cell. All right? The mixing cell has a volume of 1. What does that mean? What this mixing cell represents is a slice of water at the end of the reach, because what I really care about is what's the concentration leaving the reach. That's what I want to know. What's the concentration leaving the reach? All right. So my volume is this little slice at the end of the reach. All right. I have some flow rates. I have some runoff coming into this reach. I have some upstream flow coming into the reach, and I'm actually putting some mass. So reach 1 has a concentration of 2 species. We have 2 species we're simulating here, cadmium and zinc. Cadmium has a concentration of 1,000 milligrams per liter. Zinc has a concentration of 5 milligrams per liter. And we're adding that to this reach. All right. Reach 2 looks identical. It's got different concentrations coming in, but it's got the same idea. Reach 3 looks like this. So reach 3 has 2 inflows to it. I've connected reach 1 to reach 3, and I've connected reach 2 to reach 3. And that's the flow rate in each one of these guys. We have a certain flow rate coming in. Reach 3 is also a very small volume. This guy is going to calculate the concentration at the end of the third reach. Reach 4 looks like this. His inflows are from reach 3. His outflow is just to the sink. By the way, let's go back to reach 3. Reach 3 has an inflow from reach 1 and reach 2, and it outflows to reach 4. Right? So I've just set up this very simple system, and if I run it, I can calculate the concentration. So here's the concentration of zinc in those 4 reaches. So the concentration in reach 1 and reach 2 are constant. We set it up so that it's a constant concentration leaving reach 1 and reach 2. Reach 3 is bouncing around. Reach 4 is bouncing around, and it's been diluted, obviously. So reach 3 is also been diluted. It's a lower concentration than these 2 guys. Right? We're mixing these 2 guys up here, but the flow rate is higher. So we've got some dilution going on. Why is the flow rate higher? Well, in addition to having upstream flow into the reach, we have some catchment runoff into this reach also. All right, so there's more water. Same thing here at reach 4. There's some runoff, and you could also, obviously, what I didn't add here is there's also would be some base flow, perhaps, into these reaches. So the bottom line is we're moving downstream, and we're just diluting the thing as it goes through. And what these mixing cells are calculating, what they're representing for us, is the concentration at the end of the reach, which is what we really care about. We're going to measure it at this point in space. This is the mixed concentration at this point. After we've done mixing of clean water, of runoff, what is the concentration at this point? So this is how you would set up a stream model if you really cared about looking at the concentrations moving through this system. So what we've done here is dealt with very small volumes, but now let's do something that's a little bit more complicated. All right, so that what I've just showed you is totally appropriate if you were modeling a stream flow. And all I wanted to do is calculate a concentration at the end of a reach at some point in space. But in other types of systems, they don't work that way at all. I might just have some ponds. These ponds have large volumes. I have mass coming into these ponds. They don't respond immediately. Imagine if you're doing a mine water balance, you're putting mass into a big reservoir or some storage pond. It doesn't respond instantaneously to what's coming in. So in those cases, we can't just define a tiny arbitrary volume. In those cases, the volume of water represents the true volume of water in that pond. So what I've done here is I've set up a model in which I've got two ponds in which I'm adding some mass to these ponds. And I'm not doing it forever. I'm basically saying I'm going to add 6 grams per day into this pond for 5 days. I'm going to add 10 grams per day into this pond for 10 days. And I'm putting in 5 cubic meters per day of water flowing into these ponds. These guys then overflow, let's say, into a third pond. And then he overflows out of the system. So the concentration or the volumes in this simple model are still constant. So the volume of this guy, the volumes in all 3 of these ponds are 100. All right, so we're not changing the volume yet. All right, we're not changing the volume in these ponds, but these are not tiny little volumes. They're the real volume of the pond. Let's see how this works. Let's look at the concentrations in these systems. So open up a model that does that. It's this guy. And so there's our system. So basically I have 3 ponds. They all have a fixed volume of 100. All right. Both of these ponds have 5 cubic meters per day coming in. He's got a particular input rate of how much mass is going in. This guy's got a different input rate of how much mass is coming in. And then these guys flow into this pond. So he's got 2 inflows from pond 1 and pond 2. And then he flows out to a sink. So if I look at that model, it looks something like this. So there's no instantaneous response anymore. So this is the concentration in pond 1. So pond 1 started with no mass in it. We added mass, remember, for 5 days. And then, remember, we're having water flowing through this constantly. So we added mass for 5 days, but during the entire period, we had 5 cubic meters per day flowing in and out. So mass comes in, and then mass goes out. That mass happens to be flowing into pond 3. Similar situation with pond 2. There was more mass added, and it was added for a longer time period. And then he slowly flushed out. These 2 masses are flowing out of pond 1 and pond 2, and they're flowing into pond 3. And so there's the concentration in pond 3. If we go long enough, there's no mass in the system at all. It's all flushed through the system. Remember, these guys, I only added mass here for a limited amount of time. So after about 100 days, all the mass is flushed through the system. And our concentration goes back to 0. So here's a system where we're just doing simple mixing, but it's not instantaneous, right? There's inertia here, right? Because these guys start empty, so it takes a while for them to respond to the mass coming in and out. This is exactly the type of thing that you would see in a series of ponds or lakes or reservoirs, let's say at a mine. You wouldn't have instantaneous response to the inflows of mass. It would take some time to respond based on how much volume of water you had in the system. So one of the things I haven't talked about is how does GoldSim do this? How does it do these calculations? Let me just take a second to show you what GoldSim actually did. So in this system that we just drew, how did GoldSim solve this system? Because this is all the elements that I built. That's the whole model. I'm not doing any calculations at all. GoldSim's doing the calculations. I'm not telling it, I'm not doing any any of the mixing calculations. GoldSim's doing the mixing calculations. It's calculating the concentration. How is it doing it? Here's how it does it. When I built that system, these are the equations that GoldSim formulated. So if you think about it, there's three equations that we care about here. The rate of change of mass in cell 1, the rate of change of mass in cell 2, the rate of change of mass in cell 3. Based on the inputs to that mixing cell, GoldSim says, well, the rate of change of mass in cell 1 is whatever my input was. This was a function of time, but it was my input minus the flow rate out of cell 1 times the concentration in cell 1. Similar equation for 2, and the concentration in cell 3, the rate of change of mass in cell 3 is what's coming in from cell 1, what's coming in from cell 2, minus what's leaving cell 3. That's just the differential equation that describes the rate of change of mass in cell 3. And of course, the concentrations here in this simple system are just mass divided by volume. And in this case, volume is constant. That's what GoldSim did. So we set up, when we built the model, GoldSim in the background formulated these equations automatically and then solves them numerically. That's what it does, right? Does that for you. You don't have to write these equations and solve them. It formulated the equations, said, well, that's what defines this system. Now I'm going to solve these equations. In the model we just did, we assumed the flow rates and the volumes were constant. Right? I basically said the ponds are overflowing, and so we assume the volumes are always at their highest level. They're always constant, and the flow rates we entered as constant. They don't have to be. In a real world system, they're not. Okay. So we're in a real world system, we're going to have changing volumes. So how do we go about simulating the system that I just showed you if the volume is not constant? Well, here's an example of just that. So in this particular model, it's a little bit more complicated now. Here's what I've said. I've said I still have this pond 1 and pond 2 are still constant volume, and they overflow. So they don't change. 5 cubic meters comes in, 5 cubic meters goes out. But pond 3, I'm going to say, well, I'm going to manage that pond. I have some pump. I have a pump in that pond. And here's what I'm going to do. I'm going to say that pond 3 starts with 100 cubic meters of water. A pump turns on whenever the volume exceeds 125, and it turns off when it goes to 100. So you can imagine the pump just turns on. Oh, I'm at 125. I got to get the volume down. Turns on a pump. Once it goes down to 100, turns off the pump. And the pump pumps at a rate of 15 cubic meters per day. So I'm just kind of managing the volume in this pond. All right. It's a very simple little model, but the reason I want to do this is now this pond 3 volume is no longer constant. He's changing with time. Not only that, the flow rate out of this system is no longer constant. Sometimes it's 0, right? And sometimes it's 15. So let's actually look at that model. That model looks like this. The only thing I've done to set this up is I can no longer just put in 100 right here. I now have to calculate the pond volume. And of course, if you're going to calculate the pond volume, how are you going to do that? You're going to use a pool element or a reservoir element to do that. In this case, I've used a pool element. All right. So this part of the model right here, let me just put a box around it. This is my flow model. The whole purpose of this part of the model is to calculate the pond volume and to also calculate the outflow rate, how much I'm pumping, right? So this guy's got two inputs that are coming from the flow model. He's got the pond volume itself, and he's got the pumping rate, which is either 0 or 15. And so I've linked my contaminant transport model to a flow model in a very, very simple way, right? And there's nothing really, you know, my volume is doing this, right? So that's what the volume in that, it wasn't 125, by the way, it was 150. The volume is just going up and down between 100 and 150 cubic meters, and the concentration looks a little bit different. It looks quite similar to what I showed in my last, but if you were to look at, if I were to compare my result from a constant volume to the result with a changing volume, the results actually look a little bit different. They look like this. So here's a comparison between those two. I'm not going to get exactly the same result anymore because my volume is changing, my flow rates are changing. Slightly different result in the case where my volume is actually changing as a function of time. But the point of this model is just to demonstrate to you that this is how you link a model. This is how you build a contaminant transport model in which the volumes and the flow rates are changing. You go ahead and you build your separate model. In fact, in most cases, let's say you're doing a water balance model at a mine, you're going to build your water balance model first. That's what you do. You're going to keep track of the flows. You know how much water is in the system. You know what the flow rate is. Once you've built your water balance model, then you might build your contaminant transport model. Say, okay, now that I've got a water balance model, now I also want to do some water quality calculations. But those things have to be coupled, right? Because these volumes and the flow rates are not constant. They could be changing with time. So, in summary, what I've kind of walked through here is, you know, I gave you some very simple examples of how to use the contaminant transport module. I should note, by the way, for very simple calculations, you don't need the contaminant transport module to do a mixing calculation. So in that first, you know, you can do a simple mixing calculation yourself. The more complicated your model gets, the more species you're modeling, the more difficult it is to do that calculation by hand. And why bother doing it by hand? GoldSim will do it for you. If you've got more complicated things going on, things that we haven't talked about, like partitioning and solubility, you really can't do it by hand. You really have to let GouldSim solve the coupled system of differential equations. I do want to point out that if you're just doing simple mixing really falls into two categories in most applications. It either is you're computing concentrations at a specific point, let's say in a river, right? And in that case, I set up mixing cells that are very, very small, and they represent basically a slice, an infinitesimal slice of the river, right? Right downstream of where various, you know, tributaries are mixing. So I want to know what the concentration is at this point in the river, right? The other type of mixing calculation is when you have ponds or reservoirs that have large volumes that they don't turn over immediately. It takes a while for them to flush, and in those cases, we almost always have to link this simulation to a flow model because my volumes and my flow rates are going to be changing with time. One note I will make here is that if your volume is changing with time, for numerical reasons, you may need a smaller time step. It turns out within GouldSim is the volume in a mixing cell cannot change rapidly over a single time step. If it changes too rapidly, we run into some numerical problems, and GouldSim will actually throw an error message and say, hey, this is turning over too quickly. You need to shorten your time step. But GouldSim will tell you if it encounters that. In general, if your volume is changing in a mixing cell, you want it to change slowly in that you want it to change a small amount within one time step. Just a little aside there. Again, I also want to point out that what we've discussed here is very simple. All we've done is mixing, right? The CT module can do way more. It can deal with solubility, partitioning, decay, movement of particulate matter, lots of bells and whistles. Treatment, you can model a treatment process, lots of bells and whistles. However, for many applications, a simple mixing model is where you should start. And the reason I point that out is in many applications, you might want to deal with solubility and partitioning, various reactions that are going on. That's well and good, but you may not have the data to do that. It may be very difficult for you to justify those input parameters. And maybe the most appropriate thing you can do is a simple mixing model that represents this is what happens if we mix some conservative species. Conservative being they're not reacting or sorbing. What would happen if we just mix these species and there's no reactions, there's no sorptions, there's no solubility constraints, none of that is going on. A simple mixing model will give you some insight as to what's happening in terms of things like dilution and so on. And then if you have some data and some geochemists you can talk to, you might take the next step and deal with these very important processes that can have massive impacts on the concentrations in your system. Finally, I just want to point out, the contaminant transport module is complex. It's a pretty powerful add-on. You can build very complex multidimensional models. We've built some trivial models here. You can build a very complex model with hundreds of pathways that represent, highly complex three-dimensional systems. The contaminant transport module is not intended to model a system with 10,000 of these mixing cells. It's intended to model systems with tens or hundreds of these mixing cells, and it does that quite well. How do you learn more about the contaminant transfer module? Well, there is a user manual that's quite detailed. We have some example models in our model library. This course I'll post within the next day or two, and all the models I talked about you'll have access to. You can always send us questions, and I am currently working on a very detailed online course. I don't know if those of you who have seen our existing online course. Our existing online course just talks about basic GoldSim in great detail. I am now working on an online course that describes the use of the contaminant transport module in great detail. That's a work in progress. That's going to take a while for me to finish, but at some point that will be up there too, and that'll be a very nice resource for you to use to dive into GoldSim. Okay, well, I thank you for your time and attention, and as I pointed out, I will post this to our website. We'll have a video, a recording, and all the model files that I showed you will also be up there so you can download them and play around with them a little bit on your own. All right, thanks for your time and have a good day.